Welcome to Quantum Kinetics Corporation. I'm your host and CEO, and today we're going to be talking about what is quantum kinetics. What does it mean? What does it mean in physics? And how do we use that for thermonuclear fusion on demand? So if you're interested, go ahead and stay tuned to the end of the video. Before we begin describing what quantum kinetics is, we have to first learn, where did quantum even come from? Quantum stem from this thing called the ultraviolet catastrophe, which basically just means that all these emissions, electromagnetic radiation, seem to work out just fine in the classical sense, but when you get to a certain scale in the nanometer range, there's a phenomenon that occurs called the ultraviolet catastrophe. And so what happens essentially is the curve goes off into infinity in a mathematical classical sense, but in the observable world, we actually get a bell curve that comes down to describe the ultraviolet catastrophe and then also things that happen at the X-ray level. And so that is an important distinction to understand, where the quantum kinetics resides only in this region going forward and not in the classical sense. However, classical behaviors of momentum and inertia can also affect what happens in the quantum world as well, and we'll discuss more of that as we go forward. So now that we know about the ultraviolet catastrophe and how this relates to the quantum kinetic effects, we can actually talk about the space charge polarization that happens between two electrons as you put your hands on the steering wheel, or you put your hands on the linens, or you put your head on a pillow. The interaction space actually creates a 0.1 to zero point 0.3 nanometer spacing between everything that you interact with. If you pick up a pen, there is a space between you and the pen. If you pick up a penny, same thing. And this spacing between the two objects, your hand and a penny, is actually 0.1 to zero point 0.3 nanometers in scale, which is so interesting because that scale, it correlates to a very special photon called an X-ray. And that X-ray temperature is between 4.1 and 12.4 keV. That's very fascinating because that's actually where thermonuclear temperatures actually reside when you're doing a thermonuclear event. And here at Quantum Kinetics, our reactors emit this emission because we are actually doing a full-on quantum kinetic well phenomenon, inducing safe nuclear fusion using the arc reactor fusion on demand. What essentially happens is the field lines, the electrostatic and the magnetic field lines of the resonant electron, start interacting with each other and they push away. Basically, if you sit in a chair, you're actually technically levitating on an X-ray size scale of flotation field lines. It's incredibly important to understand that the spacing between these two space charges of an electron and another electron, this, by the way, this could be a proton and another proton. This could be a helium and this could be a beryllium. It doesn't matter. On the outside of every atom, there's electrons floating around it, right? So this interaction space, if you start getting these emissions as you're quantum kinetically pushing them together, you're doing thermonuclear fusion. It's a very important thing to understand that when you start doing this Coulomb space charge repulsion and you're DeShielding the action, you'll start seeing the photon emissions in your nuclear reactor. In a quantum kinetic behavior event with nuclear fusion, what happens is there's a Coulomb DeShielding effect, and when you Coulomb DeShield the electron, it'll actually fall inside the nucleus, causing a quantum thermodynamic change of the proton into a neutron, or even a neutron can turn into a proton. And when this happens, you actually get an X-ray emission as the electrons falling in or being pushed back, or the DeShielding the Coulomb barrier. So if you're seeing X-rays in a nuclear fusion reactor, you are successfully doing nuclear fusion. So now you're probably asking, how do you even cause a thermonuclear event to happen at room temperature? Well, it's actually pretty easy. All you have to do is figure out a way to trigger an antimatter reaction in a localized space next to an electron. And during this resonant condition, the electron will actually switch into a positron. It will appear, thus causing a negative differential pressure to occur in the localized space, and the degrees of freedom of the universe will then suck in, causing the electron to do an electron tunneling event, which is also called quantum tunneling, and the electron will fall into the nucleus, turning the nucleus into a proton, or a proton into a neutron, or either way. So when you create a negative differential pressure using the quantum kinetic well phenomenon, you have safely done cold nuclear fusion. Thanks for tuning in. If you like this video, go ahead and make sure that you like, share, and subscribe. Go ahead and hit that bell icon as well. It really helps out. Get this technology to you as fast as possible. And always remember, fusion is love, and love is fusion. You don't have to force it. It just happens.